to welcome Dr. Zingen Yao from National University of Singapore. So Dr. Yao has visited our institute like 2 or 3 years ago, right?
Yes.
To 2023.
Yes.
Okay. So we welcome Dr. Yao's return visit at this time. And today, Dr. Yao is going to introduce interaction of statistics and geometry to us. Let's welcome Dr. Yao.
All right. Thanks a lot for the short time. Actually, very short term no notice to host me to give a talk. So I think 2023 I was here, and after 2 years I'm back. I'm trying to share some of my research recently. Actually, the research I'm trying to share is actually starting from 2016. I was doing some sort of trying to extend some geometries to statistics, or maybe trying to explain some statistics to some geometers, and so that we can have some common ground to talk about things moving forward. So today I'm going to talk about this manifold fitting things that I've actually started since 2017, and hopefully I can present some of the cases in how we actually going to use this thing to some apply areas, so that we can get some sense what I'm talking about this manifold fitting. So my talk will be in very high levels, and we're just going to go over some of the concepts that I think will be important. So I'm going to start from this so-called OpenAI thing. So people are developing a lot of stuff in AI is trying to generate these things. For example, they can generate images, videos, and so on. They basically took a lot of data in and trying to generate authentic as soon as possible these images or videos, and somehow trying to impress people for whatever reasons. And there has been some major, I would say the breakthroughs, and most of the thing from my point of view is basically you have a lot of data, either they're text data or image data or videos and so on. They're trying to embed them into a lower dimensional space and do their business over there, which is okay. This is basically the common ground, how people were trying to take in high dimensional data and put them in the lower dimensional space. And then after the whole, you can actually do a lot of trainings and over there, then eventually you're gonna go back to the high dimensional space, so people can actually see it, can hear it, or maybe can view the results and so on. Different people talk about different things when it actually comes to the lower dimensional space. Some people talk about lower dimensional latent space, lower dimensional intrinsic space, even lower dimensional manifold and so on. But we're focusing on a lower dimensional manifold and trying to prove that this is a lower dimensional manifold. You can always reduce space from high dimension to very low dimensions, but how you actually going to guarantee that the lower dimensional space is very intrinsic, so that you wanted to do your business over there, and how to actually improve it? It's a manifold estimate and so on. This is basically my point of views, and we're going to talk about the fitting things, basically trying to fit a manifold behind a very high dimension, and actually guarantee that manifold will actually fit it. It has some kind of guarantees, at least theoretically. Hopefully, they're going to be useful in high dimensional data. All right. So this is just a example we just came up. For example, if you use Sora and trying to, you can see that there are some images they actually authentically generated, and you can see the the lines basically break through the glass, which means that in this lower dimension embeddings, some people at least at some point didn't do things quite well. So that maybe we should actually have a look at it, how to much more, I would say, precisely, embedding your data into the so-called lower dimensional, spaces. So there definitely has been some improvement. And I'm going to introduce the so-called manifold fitting, but this is going to be, I would say, just trying to highlight some of the recent collaborations. So my goal is trying to explain what the manifold fitting is, and this is actually attached to this paper called manifold fitting for unbounded noise data. And after 2019, I've been collaborating with some senior collaborators, essentially, for example, the STLs on various applications. I will talk about, if I have time, I'm going to talk about a single cell analysis that we apply this technology to the single cells, trying to improve the, I would say, the clustering results. When people do supervised clusterings, and they do different things. Okay, as I said, you can use whatever you can use. Try to put them into a lower dimensional latent space, and then we're just trying to fit a manifold so that every single data point in very high dimensions can lie much closer to the underlying manifold. And then after the fittings, and people can do much more beneficial things in terms of, for example, you're trying to do clusterings. And also the second goal of actually introducing this recent work called using the manifold for these data coming from this 251 variable, which is basically from this the UK Biobank, the metabolism data sets. So these are the two applications I plan to just talk about very briefly about it. All right, so this paper took me almost like 5 years to finish, and because of so one of the referee actually gave us a lot of comments, and on a false revision, he actually apologized to us. Some of his comments was actually misleading, which actually caused the whole paper went through. Actually, I would say 4 major revisions. Each time was 11 months. That's basically going to be 4 months, actually 4 years, and so on. All right, so most of the application was actually based on this 2019 to 2025 papers. All right, so the motivations. So if you've got data in, let's say, a very simple case, you've got all 3 data, meaning 3-dimensional data, and all the points are roughly trying to lie on the Swiss rows. And the different colors stands for different clusters, right? And if, for example, people wanted to do unsupervised clusterings, try to separate these guys. So what people will do conventionally is just break down, just flatten the whole Swiss row, making it, because Swiss row is a 2-dimensional manifold. So if you flatten the whole thing, you can actually get actually a 2-dimensional spaces, just like piece of papers. So this is called dimension reductions. Of course, you can use different methods to get this 2-dimensional spaces. At the same time, all these points will be lying on this 2-dimensional piece of papers. Then you can apply whatever, okay, Euclidean methods on it to do cluster creations, to do clustering. It's fine. But if you flatten the whole space, okay, and then you basically destroy the geometries, the points from here, okay, has to go through the whole spaces of this Swiss row to reach to these blue points, not just using the Euclidean distances. And some people say, okay, that's fine, but we can always find a lower dimensional space, for example, just like 2-dimensional spaces, to map the points so that they can preserve some distances. Yes, of course you can do that, but in that sense, you still destroy the geometries. Okay, so what I wanted to do for my research using the manifold fitting is that using these data points, okay, to actually recover the Swiss row first, then project every single point to that Swiss row in 3 dimensions of dimension 2 for this particular manifold, then perform this clusterings exactly on the Swiss row, not on the 2-dimensional spaces. So this is what I call the manifold fittings. And there's, as I said, many different data sets that we basically know the geometry. For example, we're talking about earthquake data. You basically can see, okay, that all the data are actually in 3 dimensions, right? And they're actually lying on the S2. For basically, in this case, is the Earth. If you believe that, you can use a sphere to model the Earth. Then every single data points of the earthquake actually on this S2s. So they has to be lying on this exactly the manifold. We know the geometry very well, and in this sense, if you're trying to fit a flow, they're traveling around this data sets, centering of this, and trying to actually following up the main trend of these kind of things. You're basically talking about fitting actually a curve, which I would actually interpret this as actually a extending a PCA from the Euclidean space to the manifold. And this is called the principal flow. So there has been some recent work trying to extend the PCA from the Euclidean space to the at least to the remaining manifold sense. Well, this is a case we basically know the geometries. And the second case is that if you have data sets, let's say M by P matrix or P by P matrix, right? Then because of the nonlinear constraints that you can view all these, vectors or actually matrix as a point on a particular manifold where you know them actually you know how to do the computings. For example, this is the very simple case. We've got a 3x3 covariance matrix. I mean, if you people do, I believe everybody here knows what the sample covariance matrix is. This is dimension 3, so essentially it's just a 9-dimensional spaces. If you line up them and you actually making it as a long vector, in this case is 9 dimensions. Because of the symmetry of this matrix, then you can actually probably shut down to R6. Well, R6 is still too big. For example, if I use P3 to be the space of the PSDs by this 3x3, the matrices. So the P3 is still just a subset of the R6. The P3 is convex, but actually not linear. So if I have 2 matrix, all right, I would say the D1, D2. Then if you do some combinations, it's not going to be in P3s. So actually, every single 3x3 matrix, covariance matrix, can be viewed as a point on a cone, that cone living in R4. So if you're trying to develop some methods, for example, if you just wanted to do classifications, then you probably wanted to develop something that directly fitting a boundaries on the cones. Well, people say, okay, I don't care. I'm just gonna work with the nine-dimensional or 6-dimensional vectors. Fine, but at the end of the day, it's just how different people see different things. If you really wanted to treat a vector as a vector, treat a matrix as a matrix, that's fine. But there's definitely some underlying geometries behind every single high-dimensional data that maybe you wanted to actually learn a bit about this. How do you actually fit a manifold or fit a lower dimensional intrinsic structure behind this high dimensional before you actually do something else? So this is a very high-level scenario, like how we actually going to do the clusterings for every single high-dimensional data. For example, you've got two kinds of images. Right, every image is, for example, we're talking about 64 by 64, so it's basically 3,000 dimensional vectors. So what people do using deep learning is that they're trying to transform every single points, every single images to any kind of spaces determined by the functions. Then they will do the whole classification in that spaces determined by their functions. So what we're trying to do is that based on all these images, we're trying to looking for the manifold that actually best approximate the data sets. Then do the boundaries, the classification boundaries directly on that manifold, without actually leaving the whole space of the original obviously the ambient spaces. All right. So I will actually talk about how we actually do this to find out this lower dimensional manifold behind this high dimensional data using the single cell data sets, and also using the UK Biobank. I would say this metabolism data sets. Okay. Let's move on. So, as I said, if the manifold is known, extending some notions from geometry to try to define some canonical concepts is already very difficult for most of the statisticians. Here, when I talk about the manifold fittings, we actually don't know the manifold. Okay, for example, you think about a very high dimensional data. Let's say in the space of let's say capital D is very big. I want to find a manifold. It's called fittings. So when I look at this thing, around 2016, I was trying to look for, do a very extensive literature search. Everybody talked about the manifold learning that was basically dating from 1990s to 2010, almost like 20 years. People developing a so-called manifold learning essentially just try to map a high dimensional data to a low dimensional data. Okay. This is, to me, is just the embeddings. They actually do not, from my point of view, all these methods do not necessarily actually estimate the manifold. So until 2012, I would say these are the maybe some very typical papers very rare paper is talking about how you're actually going to talk about this fitting a manifold behind a high dimension, giving a manifold estimators. Okay, these methods, either isomap on LE and so on. Even my friend talked about this. He actually invent this local tangent space alignment. They actually do not estimate the manifold. So after 4 years after 2012 of this Larry Wasserman's paper and so on, and Charles Pfefferman developed this together with his co-authors, come up with this method trying to estimate manifold seriously, but they do not actually give a concrete algorithm or method. And then the 2018 paper was very interesting, but again, they do not actually give a method how you actually estimate a manifold. They only prove that there's a manifold exists that you can actually try and find out and try to quantify the manifold. And I come up with this with my postdoc, come up with this paper that trying to give a algorithm to find out this manifold. And also based on this paper, we've got all these things trying to extend this techniques to different areas. So this is the single cell data sets. Just trying to give a very quick overview. What do I mean by this? Getting the clusterings on for these high dimension data. Every single data set. Okay, here we've got 25 of these guys. Right. Every single data set. These are dimensions. Basically, it's N by P matrix. So N is sample size. For example, the first row here. This data set has 704 samples. This is the dimension of the genes, which I call the dimension of the data sets. There's 38,000. So you can see that the P basically varies from 15,000 to 40,000. So, I mean, sorry, this was back to 2022. I was doing my sabbatical at Harvard, and somebody actually wrote to me, why don't you just do some very applied things that to actually promote your method so everybody can use, which means that I have to compare with different people. All right. So before I talk about the mathematics behind the manifold fittings, well, so you can basically for every single data set, we're trying to map, or maybe I shouldn't use them map. We're trying to push every single row here, okay, 704. So basically we have 704 data sets. We push every single data in their original space. In this case, is a 38,000 to the underlying manifold within this high dimensional Euclidean spaces. Okay, and we're just trying to do this clusterings after the fittings. So what will actually report the results after this talk. Any questions so far? So we're not going to shut down. We're not going to do any variable selections. So we're not going to actually pick, let's say I don't know, 100 most important genes out of 30,000. No, we're not going to do that. The only thing we'll do is fit a manifold that every single data will lie on that manifold very closely. And we're going to do this classification, so-called clusterings for the fitted data. The fitted data is still going to have the size of 704 times 38,000. It turned out that you can use a very simple clustering methods applied to our fit data to get a very, I would say, at least a very good results. Questions so far? Yeah.
The survey work by yourself?
No.
So somebody else did.
So somebody says actually okay, I have to tell you that I didn't know too much about single cell. So my student tried to download actually 60 data sets from all these big experiments. So in order to publish a paper in the PNS, they ask 25 data sets. So all these 25 data sets were actually the data from these papers, Nature Science Cells, for the last 10 to 15 years. Okay. So we have to apply the methods to every single data set. Of course, I'm not going to some of my postdoc students, they try to polish through all these important, I would say, dirty works and so on, okay, before they have to put this method into that kind of crazy matrix.
That's nice.
Yeah. All right. The second thing is recently one of my postdocs who is very interested in doing this, actually I would say extending the manifold fitting to this health data. So we basically try to use this UK Biobank. There is a particular data set called the metabolism. They followed almost 250,000 people, patients. So the blood samples, they actually sample, they actually try to use the MRI to actually analyze the biomarkers from the blood samples. So basically the matrix is 250,000 multiplied 251. So we have 251 biomarkers from the so-called metabolism data sets. Then we'll try to split them into 7 different subsets. So each subset has 250,000 observations. Then we fit every single, sorry, how can I move on? We've actually fit every single manifold for each of the data sets. And by the end of my talk, I'm going to talk about some of the important manifold we actually discover. For example, M1, M2, M4. So C1, C2 up to C7 are just the 7 data sets. Each is having 250,000 times some, I would say, some variable. The total number of the variables is 251. So I will actually discuss the results recently we find out from this particular data set. This is just another applications of using the so-called manifold fittings. So let me just very briefly talk about this statistic behind it. I mean, for mathematicians, they are actually they are doing something. For example, they're actually trying to do things based on this metric spaces. If you have a metric space, then they're trying to get an estimator for the manifold and hoping that they can control the dimension of the manifold being small d. Small d is much smaller than the capital D's. The capital D is the dimension of the space, okay, the original space. For me, in 2019, I will translate this problem into a much more, realistic problem that most people in my field can understand. So basically, you've got an underlying manifold, you have a metric on it, and you have a distribution function. So every single x is based on that manifold, is exactly on the manifolds. If you observe some noises, you basically lift the whole thing into the ambient space. So the y is the noisy data you observe. So the goal of the fitting is trying to construct a estimator from the y, not x. Okay, we don't know anything about the x. From the y's, then can guarantee that there is some kind of distance between the m hat with the m here. Okay, so we're trying to actually give an estimator so that we can guarantee the distance between these two guys, the m and m hat, can be bounded. And if you're interested, you can write a few papers. That's all. All right, just some illustrations. Okay, these are the noisy data points. The dashed line is the manifold. This is in high dimensions. The dimension of the space, the Euclidean space, is D, capital D's. So all these embedding problems try to embed all these points in black so that you're arriving at the red points. Once you are here, you can't go back. That's all. You're ended up into a lower dimensional space or latent space, whatever you call it, based on some loss function and so on. But you can't go back. What we're trying to do is basically try to map all these points, or I would say push all these points to the underlying manifold as close as possible, and trying to guarantee the distance between the red ones with the dashed manifold. And in order to map, actually connect some of this, actually this is a discrete setup. In order to in order to adapt this framework to some of the very early work of STL, then we can actually fit a very smooth manifold, make it a continued domains, and you can do samplings on that underlying manifold. That will be very interesting. And this is still a ongoing work and so on. All right, so the model here, the statistical model here is that we've got a data sets yi's and this xi's uniformly sample on this manifold. And people are, some people, they say, oh, can you make it much more, they didn't really like the IIDs, and of course you can still change the assumptions, but so far this is back to 2019, so this is just going to be IID sample uniformly from the manifold. M is small d dimensional. You can either use a C1 or C2 submanifold, and the reach of the manifold has to be at least a lower bound tau. So the Gaussian noise, for example, any noise here, specifically we can deal with unbounded noise, which is very important. The density is this guy in the ambient space. So the Y basically is the convolution of the two measures here. One is the noise, the other is the measure on this the noiseless data on the axis. So trying to give a estimators for the yi's to get a yi hat. We hope that y hat will be very close to the manifold. This is basically the idea of doing the whole business here. So I would say that Larry Wasserman's paper, based on, I would say starting from 2012, they rely on very restricted assumptions. They basically assume that every single, basically the thing, when I say it very restrictive, is that they assume that the noise here is orthogonal to the tangent space for every single data points. And also, most important things, they assume that the noise is bounded. Well, of course, when the noise is bounded, basically you are talking about the noisy data around basically a tube, a very tight tube of the manifold. And of course, you can still construct a manifold estimators. Though this is not too surprising, but still, these are very early work of the manifold fitting. That's why I actually put them in the previous slides. When they come, it actually comes to Gaussian noise, then they've got this minimax bound. Basically, is 1 over log n, and you need a huge number of data points so that you can get a reasonable convergence rate, which is not too convenient. That's why they stopped at around 2014. Talk about it. They're not going to do manifold fittings. And the thing I wanted to talk about for the Pfefferman's very interesting paper is that they basically lay down this basics why how people are going to do the manifold fittings. So suppose this is the manifold that you are trying to construct a estimator based on which, and these are the data points yi, yj here. And talking about the manifold fitting in high dimensions, what you wanted to do specifically is giving any point y can be any sample point or any point you wanted to project to the manifold, reaching to a y star. This is the goal. Okay, now how do we do that? So basically, you actually look around with a radius here. The radius is square root of the sigmas. And sigma is the level of the noise. So if the noise is sigma, okay, and you wanted to get the radius at the level of the square root, so that when you compute the PCA within this local stuff, you will have at least some eigengap. So this is the radius, and they need this number of the noisy points in order to actually do this job. So for every single yi, yj within this radius, the Euclidean ball basically, right? And you can construct how to project the points, the y here, using these informations. The dashed line are the the matrix. So you will get these, red arrows, blue arrow, directions. Eventually, you can do this so-called weighted average of these vectors. These vectors are just the shooting, obviously the directions. They're just one-dimensional arrows. All right. And then you have to do one more projections to project this summation fy's shooting towards the y star. So the so-called manifold estimator is that if you can actually get every point in this ambient space, not small d, the capital D here, right? So after the second projections, you can, if you can make sure that the norm of that vectors, okay, this black ones, is 0 or very, very small, then you're arriving at the manifold. So this is basically is the 2018 Pfefferman's paper. And they guarantee that the whole so-called distance between these manifold estimator and m is roughly at the level of r square. So r square is basically the sigma here. So O sigma is basically the bond for the distance between the manifold estimator and also the original m here. There's some I actually summarized this thing as using kind of two-dimensional visualizations. For example, the circle is the underlying manifold. You have some points here, right? And the green dots are the noisy points. You want to construct the estimators for the circle, basically. So what you wanted to do is trying to use all these I would say the epsilon net, trying to cover all the data sets. And within each of the epsilon net, you can do PCA or whatever you wanted to do, trying to get some lower dimensional linear subspaces. And these blue ones are just, I would say, for example, use PCA that you can within each of the Euclidean balls. These are the local structures. So what you wanted to do is trying to paste these things together, in order to get a construction for the circles and so on. For example, you can now forget about all these data points. These are all the computed local, I would say, the linear subspaces, either from PCA or from whatever you wanted to use. And for every point y here, you want to project them. This is a circle at the radius of the square root of the sigmas. Then you want to use, for example, this one using the three linear subspaces, because these centers are actually within this radius here. These are the yi, yj I was talking about previously. These are the arrows, shooting directions, and you want to use a weighted average of these guys. And you want to do one more projections, so you can see that this picture summarized for every single point on this two-dimensional images in order to construct a two-dimensional circle. So one-dimensional circle on this two-dimensional images. The norm of the last projections, the blue stands for the norm is big, the light color stands for the norm is small. You can see that using the particular algorithm, from my understanding of the Pfeffern's paper 2018, this makes some sense because these areas stands for the points that you can easily construct, the manifold estimator, because the color is very light. Okay, and first of all, the paper of 2018, they didn't actually provide anything. Okay, we are the one actually coded up that paper. So I thought 2019 this is okay, but the performance is not too good. For example, if even you actually look at these things, so for all these things, okay, even the color is very light, the norm is still going to be not very close to zeros. So I thought even for unbounded noise, okay, if you look at around this Euclidean ball here, around this y here, okay, you don't really have to do this, two-step projections. All you have to do is just do a Fauché mean. I would say the average of the points within the Euclidean ball here. Fauché mean is just one of the sample means we can talk about. And the y tutor here, even if the yi, yj coming from the data which has a unbounded noise, right? The summation is still going to be very close to the tangent space around the y star, no matter what. And then you only have to do one-step projections and making sure the norm becomes zero. Then you can arrive as the manifold estimator. And this is the essence of our 2019 paper. And the geometry is very simple. Pfeffern's 2018 says, okay, you're shooting all these things, combining all these blue and red arrows, eventually get the black arrows shooting down to the manifold. Eventually, this is the bias you always going to have. So my thought was, okay, I'm going to do this average for all the data points within the Euclidean ball, and then getting, for example, a rough estimator B. The B could be the y tutor, just a sample average of the point of Fauché mean or whatever. And then this tangent, this space here will be very close to the tangent space of this particular point on this manifold. And all I have to do is get this orthogonal shootings. And this one, the bias is very, very small, much smaller than this one, even from these pictures. That's why the method worked, but the method doesn't actually improve theoretical the bond. The bond is still at O sigma. Okay, the bond is still at the level of the O sigma, to guarantee the manifold estimators. So 2022, the whole world is fighting COVID. So we got this sort of ideas. Actually, this is actually trying to compete with some of the Pfeffern's 2022 papers. In order to project the point, for example, any y to the manifold, hopefully it's very close to the manifold itself. So the blue dots is the one from our 2019 papers. The O sigma bond is the best that we could do back then, okay? Or if you write the papers trying to push this one to the manifold, this is probably something you will get. The blue dots. The question is, can you push it further to get a better bond? For example, if the sigma is very small, can you actually improve your work theoretically to get a better bond? The question is yes. So how are we going to do it? Most of the people talking about the local data, they always say, okay, we sit here looking around and getting Euclidean ball, neighborhood, whatever, do something. The question is that if you get a Euclidean ball, you can't really beat the PCA because of the eigengaps. So what we're trying to think about is that we're trying to construct a cylinder. This is also similar as the Pfefferman has done in 2022 paper. So this is a cylinder where it's essentially just the product of the spaces. Sorry, two spheres with this R1, R2 radius. So the rationale is here. If I truncate the points, these grid points within the cylinders, if we're trying to shrink the cylinder, making the cylinder becoming thinner and thinner, then the main axis of the cylinder that you're trying to construct could be very close to the ideal projection. You want to further push the blue dots to the manifold. So we call this from the blue dots to this green one, we call this step as a local constructions. We can actually prove that the local construction can push the points blue towards the green, and so that we can get a roughly, I would say the roughly sigma square bond. This is the some kind of improvement based on the 2019 papers when people talk about the manifold fittings. And the actual idea we're using is that we're trying to, for example, the Fy here is the blue dots. We're trying to control the angles between the blue dots minus the Y with the Y star. Y star, the ideal projections we never know. So if we can control this, we can actually get the bond at the sigma time the small octaves, and plus the previous O sigma, we can get the sigma squared times this little terms here. So the why this is important, because if you're using PCA, if in order to get the eigengap, you can only get sigma square. That's why, you can only get the sigmas. That's why this is combining with this technique, we can actually get the sigma square. So this specifically, we can get a sigma square times this log term. If this small, then the whole log term can be ignored. So roughly, we can get a sigma square. So we think this is important when we look at this the manifold fitting problems. And I will skip some of the details and just talk about the directions we're going. So 2014 to 2019, I focus mainly on how to extend the different notions from the geometries to the manifold. We basically know the geometries, and after that, 2019, 2020, 2022, this area, this period, we're actually developing the manifold fittings. Then these are the stuff that we are extending the manifold fitting in different areas, such as machine learning, single cell analysis. Recently, we've got a cell scope and try to build up the pipelines, analyzing the so-called single cell or DNA whatever project. And then this is the 2015 metabolism data set, which I'm very briefly going to talk about. So before that, I just wanted to mention the CycleGAN business. 2023, I organized a conference January at Harvard, and someone who told me, okay, if you want, why don't you just combine your fitting, two-step fittings, to the machine learning people? Well, I have to admit that I didn't know too much about the GAN, but I did some search. So the GAN basically, for example, we're choosing the CycleGAN, but there's different kinds of GAN basically. So the CycleGAN try to learn a mappings between the lower dimensional space to the high dimensions. For example, Y can be images, can be whatever high dimensional data. Z can be lower dimensional noise, for example, Gaussian noise. You're looking for a mapping between these two Z and Ys, and try so that if you can generate some mappings like this, so you can basically construct some, you can basically generate some fake images trying to fake the Y at all. So the GAN has somehow learned a cycle here. So the GZ, GY are the generators. These D are actually trying to discriminate if the thing you are generating is fake or not. So if you can cheat the whole system, you actually eventually you can return a balance so that you can generate some images. So I thought, for example, if this is a lower dimensional Gaussian noise, you giving a trained generator, you can generate these fake images. The Y are the real images. I mean, that's fine. But all the Ys, regardless it's fake or not, they're in high dimensions. So if I can push all these Ys, regardless they are fake or not, to their underlying manifold in the original ambient space, not doing dimension reductions, before I pass them to the discriminators, that might actually improve the convergence or the speed, whatever. So we actually just put a manifold fitting on this Y spaces, because these are in high space, high dimensional spaces, before we pass the results to the DYs. And hopefully this whole thing will, help this whole GAN, cycle GAN, to operate. And eventually after the trainings, you can actually get all these GZGYs, and so that you can actually get this manifold estimate and so on. So this is just a applications of combining the cycle GAN with the fittings, and eventually you can do interpolations in this manifold. Then eventually gonna go back to the previous page. Then you can actually go back to the Z here. Sorry, this is picture stuck here. So if I can generate some, if I can finish the whole trainings, then we can actually do the interpolations on the Z here. Z hat here is the so-called latent manifold. And then you can do the interpolations here. You can do whatever you wanted to do, and then eventually you're gonna get all these realizations. So I will skip the applications for this framework because there are just some simulation data. So one more thing I just wanted to mention is that, for example, this is still a simulation data, how to improve the cycle GAN. So these are the images. You've got 7 times 7, so you get 49 images. So not only we can do denoising, pushing all these images to the underlying manifold at some point to denoise data, but also if you fit these two guys, okay, so we can actually generate 1, 2, 3, 4, 5, 6, 7, actually 14 images between these two folks. And we can generate them directly on a lower dimensional manifold. So these images were not observed in the whole data set. This is what I call interpolations. All right, so I will skip some of these. So this is a single cell applications. This is actually first row of that 25 data sets. Okay, 704 multiplied 30,000. So the technicians determined that there are 3 clusters based on something that they basically use. So we didn't use the information of the labels. To us, it's just 704 times 30,000. Okay, so we can only see things in 2-dimensional or 3-dimensional. So for the 704 multiplied 30,000, so we can visualize them first using anything, for example, t-SNEs. These are just map all these points into the 2-dimensional spaces so you can see them. So because we know the labels, you can color them. So you can see that they are actually mixed together. So in order to do a clustering unsupervised, then you will say, okay, let's just do deep learnings to tune all these things you wanted to tune. Okay, eventually you're probably going to reach 99%. That's fine. So what we did was just fit a manifold for the 704 multiplied 30,000, return you the 704 multiplied 30,000. Then you've revisualized our fit data set using the same t-SNEs, and this is the results. Again, this is the first row of that 25 data sets. So you can see that for this one, okay, this is just what we got by visualizing the fitted data set. We didn't do any clusterings. You can do clustering, not us. So this is just a visualization. You can see that because we know the labels, so we can color them. So you can see that these 3 clusters or maybe 4 clusters are already separated. When we visualize them, well, this was, as I said, 2022 December at that time. I was very surprised. I thought it was just a coincidence, because people will say, okay, so what? You can still do the deep learnings, whatever. This will be, reach to 99%. But for this one, if you just simply do k-means or actually hierarchy clusterings, you can already get 100%. This is because the referee asked us to do many things, okay? So these are the 25 data. Okay, this result was still back to 2023 January. Okay, we've got the actually the new results, but this was back then. So somehow we had to compare with this paper because they asked us to do that. This paper used autoencoders. Basically, autoencoder is that you have a known models and trying to do the tunings to map the two different spaces, okay? And then you can see that all these red ones are the performance after using the manifold fittings. And over the 25 data sets, you will see roughly 25% improvement in terms of the index ARIs, not in terms of the so-called misclassifications. If you are just relying on the misclassification, we can actually improve much higher. All right, so I thought that if we are doing this thing over 25 data sets using the fittings, then if we can improve, even beyond the so-called autoencoder methods, then there must be something we actually did much more corrected than most of the people did. All right, so this is the single cell stuff, and this eventually we're going to do this so-called pipelines. If you give raw data to us, do some transformation just as everyone else in the whole single cell business. The only thing we are doing different is that we do a fitting, return you the same dimension of the matrix, then you based on the matrix, any single very simple unsupervised learning clusterings, classification methods can be applied. Then you can actually achieve a better result, hopefully. So this is the pipelines, and we'll just skip some of the stuff and just directly talk about the metabolism stuff, the data sets. Again, 250,000 patients. So the total variable are 251. So we split them into 7 different groups. So we're fitting a manifold for each of the data sets. Return you the same dimensions for each of the matrix. So we'll be actually getting M1, M2 up to M7 for each of the original data set. I'm only showing you some of the results. So M1, M2, M3, M4, M5, 6, these are the all the fitted manifold. So I'm going to show you the results for M1. M1 is 250 multiple, let's say, I forgot the exact number of the variable, maybe 30 something. So this is a small matrix, not too small, but in the huge matrix, but with, I would say, the 16 or actually 30 variables from the 251s. I will visualize the fitted results for this M1 matrix. And this is the result. Again, we're only visualizing 50,000 because if I visualize 250, it will be the whole images. So we're picking 50,000 uniformly random sample points. It's a small subset of the samples. If you're using all these methods, okay, deep learning, whatever, trying to visualize in a two-dimensional spaces, this is what you usually got. So we did the manifold fitting and visualizing 50,000 people for this guys. This is what we got for the M1. Be careful, this is just the M1 results. So now you can see that the M1 actually has 2 structures, 2 clusters basically. To me, just 2 clusters. One is the big, this big guys here. There are actually 50,000 people. Okay, so the whole, the outside clusters has 46,000 people. This inner inner structures has 4,000 people. So yeah.
Hello.
Yeah.
Clarifying question.
Yeah.
So one dot for one sample.
Yeah.
Oh, okay.
So we have 50,000 people, but we actually train the manifold for 250 points. But I cannot visualize the whole thing in this square because in that case, it will be everywhere.
Okay.
Yeah, we only pick, let's say, 25%.
Okay, so another clarifying question. How do we know the information of C1 to C7? I kind of...
That's a good question. So basically his question is, how do you choose the variable for each of the clusters? So for each of the subset of this metabolism variables, right?
Yeah.
So basically we run I would say the clustering methods for the variables in order to pick, like, within the C1s, all these variables actually has a much higher, always see the correlations, and C1, C2 has a very low correlations. You can try the whole 251 as well, but we just pick the 7 different groups because for the 251, many people write papers, they pick only small piece of variables using, so basically follow their lows.
That's data-driven information. C1.
Yes.
Okay.
Yeah.
Thank you.
Yeah, thank you. So again, so there are actually 4,000 people here. There are 46,000 people here. The natural question is, so what? You can cluster the people into 2 clusters. Well, yes, but interestingly, the UK Biobank, we know everybody's medical profiles. So there are actually 1,000 different, I would say, diseases. So we looked at the first 50 most concerning diseases, for example, including high blood pressures, whatever cancers, and computing the risk for every single people here in the inner cluster, computing the risk for all the people here. It actually turns out that for the first 50 diseases, the risk, if you just simply run a Cox model, whatever, these people, on average, these people having one of the 50, most concerning diseases, the risk is much higher than these, the 46,000 people. And be very careful. We didn't use any medical variable to run the clusterings. We only use 250,000 multiply 251 metabolism variables to cluster the people. Now we can cross-check them using the medical histories and compute the risks, and you will see that the significant difference between the inner cluster and the outer cluster in terms of the people getting one of the 50 concerning diseases. So these are basically the findings from our recent work on the metabolism datasets. And I think that if you're interested, you can still download the paper. But these are the hazard ratios between. I was talking about this in terms of risk. In terms of the risk, sort of the differences. So I guess the most interesting thing is that at least our method can cluster people and in a very reasonable way, and then we can still cross-check them. Actually, the referee asked us to compare this method with different, I would say, the autoencoder that we only find these structures when we used the autoencoders stuff. We can't really get the clusters. So I think that's everything I want to share today. And thank you very much for your attention.
Very nice presentation, and you motivate manifold learning very well, I guess. I think manifold
fitting.
Manifold fitting. Okay, so I always think manifold fitting is a kind of very technical subject, but you motivate this subject very well, I guess. So do we have any questions from the audience? Okay.
Thank you for a very nice talk. So I have a couple of questions.
Yeah. Okay. Yeah.
So in your preliminary section,
yeah,
you mentioned your algorithm is a weighted average approach.
It's not quite weighted average, but the first step, I mean, you can understand them as a weighted step, weighted average, but the weighted average in terms of putting all these linear subspaces together,
yes,
so that they can form some structures.
Yeah.
And the important thing is to prove that the weighted average of these subspaces is indeed a manifold, and that was our intention of doing this manifold fittings.
Yeah, and I thought about the algorithm quite popular in the CS community called mean shift algorithm. So I thought in that part is very similar, but you have different weights. You apply different weights, and you apply the neighbor size first. Right? You enforce they only by the circle. So is this because of the theoretical bounding you want to?
Yes, but also I can tell you more about the mean shift. So mean shift has been there for a long time.
Yeah.
Actually, a few of my friends was working on the mean shift very extensively. So I can tell you, using this previous example, the circle examples, so mean shift works well if you are dealing with data in low dimensions. Actually, the mean shift does not converge to the underlying manifold. There's a gap between their convergence with there's still a bias here. So, for example, using this circle case, so mean shift somehow will get a circle, and that circle has a bias with the ideal circles. Okay, this is the first ones. You can actually view the mean shift as one of this, I would say, the ridge regression. The ridge estimators. But the fundamental difference between the thing we did with everybody else is that the mean shift or whatever method, they're stuck in this high dimensions because they have to go through the tangent space, basically. So the tangent space using the Euclidean, I would say any data set that I just talked about, when the P goes up to 5,000, you're basically will have a much difficult jobs to actually do the mean shift. So our methods, why is quick? For example, this for the single cell. Why we're dealing with 15,000 to 40,000? We're still very quick. We're quick than everybody else. Is because we actually bypass the tangent space estimation. So tangent space estimation is restricted to the local. I would say this. The noise distribution and so on. When you go beyond 5,000, computing doing the SVD is basically no hope. So that's why we are not using it. So maybe I didn't talk about this very specifically. The real reason of this method is that we're not doing the tangent space alignment. So if you do tangent space just like everybody else, if your P is very big, okay, you basically we're stuck here. So we're doing the orthogonal projections. So they're going to get you much further, closer to the manifold without sacrificing the cost of doing the so-called mean shift or tangent space. Basically, tangent space estimation is the problem you can't really go beyond O sigma level. Yeah.
And also, so when you try to implement this algorithm to deep learning framework, in this step, when you computing the weight, you need iteration, right? Because the weight depends on the weight depends on your output.
Compare with, you mean what deep learning?
When you put into the GAN or
yeah.
So when you feed this frame the data, did you feed the data Y or GY into this architecture?
We fit the manifold for the Y. We'll only insert a step to fit in the Y to get to actually letting all these Y's in their space.
Yeah.
To line much closer to the manifold, no matter what it is. So we just fit the manifold here. We didn't touch the GZGY. We will let the whole GAN to train the GZGY.
Oh, yeah.
We didn't touch anything about this. Yeah.
Otherwise, the back projection will have some trouble.
Yeah.
And I think the reason that you mentioned that reviewer asks you to do the experiments on so many data is that as long as you keep your result in so high dimensional presentation, it's very hard to interpret the data.
That's true.
Right?
Yeah, that's true.
Yeah. Even you cluster the population into two groups, but it's very difficult to say that what's the difference between these two groups.
Yes.
So you need to do more to to communicate with the so
we actually collected 60 data sets, 60.
Yeah.
And then we only use 25.
Yeah.
And because they said 25 is enough, so we just use 25.
So I guess that's a very typical problem in this kind of approach, like the deep learning approach, because the dimensionality is still, you keep the dimensionality so high, and it becomes very difficult to interpret the result.
Right.
Yeah. So I guess that's the maybe that's the challenge of this approach. And again, when you present the data in t-SNE presentation, in fact, by default, the t-SNE, they use PCA. So
by default, what?
When you run t-SNE,
the
default in the algorithm is using PCA.
Well, I didn't run the t-SNE. My student ran the t-SNE. So they basically use the t-SNE packages.
Yes.
So which I know anything about it.
Yeah. So in fact, in the presentation, they have applied PCA already.
Okay. I mean, this
so it's not on the real. The t-SNE is not really running on your so high dimensional.
Maybe they've done some kind of PCA first to shorten.
They cannot.
So that's why you're raising a very good question. That's why for the cell scope where we have been developing, so we didn't actually the cell. Maybe I should talk about the cell scope, but I can't really go back to this slicing for some reason. This thing's not working. It's very slow. Our original cell scope basically trying to put up a step replacing the PCAs. So your point is that if I run the t-SNE package within the package, they've already done some PCAs. Okay, maybe you're right, but anyway, we're just showing, okay, if I have the dataset MIP or the fit dataset MIP, I use the same package. What's the difference? This is what I said. Yeah, I admit I don't know anything about how to run a t-SNE. Actually, I'm not the one who did the codings. Yeah.
It's just for fun.
Yeah.
That time I remember that you also try to do application on cryo-EM data, right? But today I did not see your result.
The cryo-EM is still having actually one of my PhD, when he graduated, he didn't continue. He's Singaporean. He didn't want to do anything. He just wanted to get a job. And then my other PhD, who's recently they joined recently, and he's still going to work on the cryo-EM project. So far we haven't done anything fantastic, so I didn't choose to talk about this.
Yeah, so I'm interested to know what kind of challenge you met when you tried
simply because the signal to noise ratio is too small, and then we had to do something to polish using the fitting for the data set. But the thing we got is maybe because we didn't remove the noise too effectively. So eventually we're going to compare with the reconstructions of the 3D particles and compare with some of the so-called deep cryo or something that we didn't have a significant improvement. That's why I didn't choose to. Maybe next time come back here, I'll show you some results. Hopefully my current student who didn't quit.
It's nice to hear this comment because I'm doing on cryo-EM.
Okay.
So your comments will let my colleagues know how challenging this project is.
Okay. Okay. Yeah. Thanks.
Thank you for the questions. 我们的讲者也是讲中文，所以如果大家有想要直接用中文提问，其实也是可以。因为我刚在暑假有时候就是年纪比较小的实习生。
对，因为我刚才想用这个中文演讲，但是他说因为有人不会英文，所以我只能用中文。
Okay.
So
Thank you so much. And then I just have a very small question. So all your like proposed methods are based on the kind of like a non-parametric method. And then if you want to have some kind of like a semi-parametric or parametric kind of like restriction, do you think you're like you can improve in terms of the late conversions? And then also the I think your assumption is like your points, your data points are sample uniform IID from the unknown manifold structure. And then I mean, it would be the case, but I'm like sometimes you do kind of like a preference sampling. You sample more on the place that have small curvature, so you want to know
Yeah.
the structure. And then the bounds you get is kind of like a global bound entire manifold. So
Yeah.
if you have some kind of like, I mean, it might not be realistic, but if you are able to sample more on a point that have, for example, like a small curvature, then do you have kind of improvement on this?
No, that's the actually you asked 3 questions, but I'm trying to answer a few of them because this is really related to some of my ongoing research. So the mathematically, okay, so far we've just say, okay, there's a data set. We're looking for a manifold that somehow represent the data very well in terms of geometries, but most of data sets they don't. I mean, you can always fit a one single manifold, just like you fitting anything you using the least square. You can always do whatever you want to do. But actually, there's different cases. You can actually fit a collection of the manifold. For example, you can fit 2 or 3 manifolds that people talk about as a stratification of the manifold. For example, you can think about there's data sets. You can fit a seed pattern with a line pattern together. So now you can think about fitting two manifold within the whole data set. And with each of manifold will be fitted differently according to the curvature of actually the data distributions. So these are still ongoing work. I don't know the answer, but we're trying to do something out of it. Basically, trying to fit a collection of the manifold, not just a single manifold, to accommodate the assumption of the heterogeneous of the noise. Most of the noise, from my point of view, is different from most of the people in statistics. The point of view that why the problem is difficult, why the manifold is necessary, is because of curvature, not because of noise. For some of the areas with if you have a significant different curvatures compared to someone else, you compare it with somewhere else, you do need it to fit a different manifold. How do you combine the 2 pieces of the manifold together? This is called a surgery. We still are. I mean, we're actually one of my recent postdoc who actually just joined last month. We're working on this, but I don't have any results yet. She's from pure math, but we just talk about stuff. Yeah, but this was actually done by some of the very earlier job that Professor STL has been doing, but I'm still trying to understand his paper. It's not actually, to me, it's too difficult. I mean, I'm still trying to understand and putting them into a continuous domain so we can do many things. Yeah, and the ID assumptions. Many of the referees asking me about the ID. We can actually take off the IDs, but again, to me, it's just not write just another paper. So ID is okay, but we can use some probability bounds. Without ID, we're stuck, but we can still perform the algorithms. We can still perform the algorithm. It's just like maybe the results is not a manifold. That's all. But in order to improve the results is a manifold is already beyond most people. Some people just say in computer science, for example, he mentioned this. What do you call the method? Lemming shift. It's just a way that you have a loss function and somehow you do it. There's nothing control. Okay, for example, I have a tree data, all these space data. Nobody knows the outcome of it. You can't even prove it's a manifold. At least we can prove it is a manifold from this particular setup. And if we change the setup, we have to see what we can do in order to theoretically to actually claim to actually get something else. Yeah, but right now you can simply use our algorithm to polish whatever you want to polish the data. Yeah.
Hello, any question from online audience?
华文也可以了。
看不到线上有人问问题，左边啊，我看不到啊，应该看起来好像有看到 ，OK， 应该没有吧 ？OK， 好啊，那今天演讲就差不多到这边啊，谢谢大家参与啊，谢谢我们的讲者，你看。